Right. Hello and welcome. In this example, we are going to determine the voltage drop across our series capacitors. So we have 3 voltage drops total. We have VC1. We also have a VC2. It's the second voltage drop. And we have VC3. VC3. Right, those are the voltage drops across each of our series capacitors, and we know that in series KVL is the law that we utilize. KVL, and that is going to allow us to use our voltage divider rule. And so we're going to do the same thing that we usually do for series resistors, but we got to remember that voltage is different for capacitors in series. Right? So each time you use a capacitor, it's a little bit upside down from what we did with resistors. So in this case, we're going to say that our voltage divider rule for capacitors in series is going to give us VC1 is equal to our total capacitance on top, CT, that's different, divided by our capacitor on bottom, C1. And that's going to be multiplied by our voltage source, right? So this kind of plays along with our current divider equation a little bit too, where our current divider equation kind of flipped this upside down as well. So try to keep them intact, try to keep them all separated. This is for series capacitors. Okay, so we'll set this in here, and we know most of these. We don't know our CT yet, so let's fix up our CT. We can actually do that by moving C3 into a picofarad, right? Because all the other ones are in picofarad, so we'll move C3 into picofarad and say it's actually 250,000 picofarad. And we'll calculate out our total capacitance using that. So we'll say our CT is equal to 1 over 1 over our 460 plus 1 over 100 plus 1 over our large number of 250,000 picofarads. Right? That means our answer is also in picofarads. And so we can do that here. Say that our VC1 is actually equal to 82, or no, that's our total capacitance, our CT. Right, so our CT is equal to 82.1 picofarads. So we'll plug that in for our equation here now that we know each one of them, and we can say that our VC1 is equal to CT, we know that, 82.1 picofarad, divided by C1, which is 460 picofarad, and we'll multiply that entire thing by our voltage source of 12 volts. So note that these picofarads are going to cancel out on top and bottom, and so you'll just divide that ratio out, and your answer can be ignoring that picofarads completely. Right, so we'll just say 82.1, ignore the picofarads, divided by 460, and that gives us a ratio equation, about 17.8% of our total voltage here, so we'll multiply that by the voltage itself, which is 12, and that gives us our answer, our voltage drop across C1 here. And that gives us 2.14 volts, right? So VC1 is 2.14 volts. We can do that for each one of them just by swapping out our lower capacitor value, right? So if we wanted to go for C2, we would put C2 in for this bottom equation instead of C1. So let's do that. We can even just use the same equation here. Instead of 460, we want to put 100. Right? And that gives us the voltage drop across C2. It's now 9.85 volts. We can do that one more time. This bottom equation here, we'll put in that giant number on top, that 250,000. And that's going to give us the voltage drop across that last capacitor. Not a lot. All right, we'll move that decimal point over 1, 2, 3 spaces. That gives us a 3.9 millivolts, really small voltage, right? And we know KVL says we can add these together. So let's try that. Let's make sure we got the correct voltage here. So we'll say 2.14 plus 9.85 plus 0.0039 gives us just about 12 volts, right? And that checks off our KVL. Right, let us know if you have more questions.